Hello everyone, thank you for your time and thank you to the organizers of CCGrid for allowing me this opportunity to speak to you. My name is Mikel Gjergji and the paper I'll be presenting today is Characterizing Input Sensitivity in Tightly Coupled Collaborative Graph Algorithms. So graph algorithms are at the core of many data-intensive applications in many different computational domains. This includes cybersecurity, medical informatics, business analytics, and social data mining, to name a few. And massively parallel GPU graph analytics yield impressive results, but the irregular graph structure hinders the full performance that we can actually achieve on that hardware. So in this plot here, we have two different implementations of BFS, where one is an independent implementation and the other is the collaborative implementation on a unified memory system. In the independent implementation of the BFS, the CPU and the GPU are working independently on different partitions of the graph without any coordination, and there's no allocation in unified memory. While in the collaborative implementation, there is allocation in the unified memory and collaboration. And we see on the independent implementation of BFS, if we look at this line here, basically the x-axis is many different graph inputs, and our y-axis is the performance of our BFS implementation measured in GTEPs, which is billions of traversed edges per second. And we could see that ideally what we would see here is that the performance would be the same for everything. We would basically the underlying hardware would be performing at maximum efficiency, and this would be a flat line. But in reality, different graph inputs lead to orders of magnitude difference in what the actual performance ends up being. And we could see this by this drawn slope here, where there's completely high variance, much greater difference between this graph input versus this graph input, where this graph input performs very poorly, while this graph input performs ideally. And this variance, this change in performance based on a graph input, is even worse when we look at collaborative implementations of these algorithms. And we could see that by this much more drastic slope that occurs for the collaborative implementation of BFS. This performance difference is so great that the worst input for the collaborative implementation is a difference of 91 times from the best input. So we have two goals going into this paper. Firstly, we want to explore this input sensitivity using machine learning techniques and try to answer the question, what are the factors that are causing this performance variation? And then our second goal is, after we find these factors, to minimize the variation by tuning some software and application parameters using an auto-tuner from some machine learning models. So the first thing that we do in this overview of our paper is that we need to actually define some performance criteria that we're going to look at for when we're training our machine learning models, exposing tunable control parameters, etc., etc. So we start off by defining some performance domains. For example, a performance domain that we want to look at is data movement. In a unified memory system, data movement is obviously very important in terms of impact to performance, because you're migrating data from device to device, say CPU to GPU, over a low bandwidth and a high latency channel. So that can cause a drastic difference in performance depending on how you're moving that data and the data volume that you're moving over that low bandwidth channel. And some other performance domains that we look at is achieved parallelism and memory hierarchy utilization. And then for each of these performance domain, we need to define some specific criteria that correlate to this performance domain. So for example, data movement, we have data volume, access patterns, and oversubscription. And then for these specific criteria, we have metrics that correlate to it, such as copy to comp ratio for data volume, access density for access pattern, etc., etc. And then for these specific metrics, we can define some specific CPU and GPU events to actually measure for these metrics, which are listed here. So now that we've defined some performance criteria, the next thing that we want to do is select some of the dominant performance criteria. And the way that we do this is by filtering the performance criteria via regression. To do this, we construct a regression model to correlate specific inefficiencies, and our explanatory variables are the metrics from our previous table, as we could see here, listed again. And the response variable is the performance, which is measured in GTEPs. So we get some of our metrics eliminated via PCA, and then some via our regression model are insignificant. And in this section here, we have some performance metrics that are deemed significant by our regression model. In these significant metrics, we could see that some are not performance critical, and some are performance critical but have a low variance, so there's very little wiggle room to work with here. And finally, we have three values here: occupancy, access density, and register efficiency, which are performance critical and have a high variance, meaning that these are highly input sensitive and we would want to look into it. So once we have our dominant performance criteria, we identify three optimization techniques to mitigate the performance bottlenecks that we identified previously with our regression model. Data placement for access density, launch bound selection for occupancy, and register allocation for register efficiency. So for our data placement, basically we have we just need to identify data structure allocation and deallocation sites and insert some clauses to handle this with the data placement that's selected by our auto tuner. And for thread block size, similar idea, we get that from our auto tuner. And for register allocation, the NVCC compiler supports a max register count flag, which can limit the number of registers allocated to a kernel. So we have some notion, we define eagerness, where moderate is the default number of registers, and conservative is whatever the register count was in moderate minus a number of registers, while aggressive is whatever the moderate value was, and instead of taking away a number of registers, we instead add a number of registers. So applying machine learning. Now that we have our exposed tunable parameters, we can build a machine learning model to perform the auto tuning for us. And to do so, we basically take two different approaches. The first approach is to use decision trees, which takes as input a graph feature vector and maps that graph feature vector to some optimal configuration. Our second approach is a redefining of the problem, where instead of predicting the optimal configuration given a graph feature vector, we change it so that we put a pair as input, the graph feature vector and the configuration, and our MLP predicts basically redefines it into a regression task where it's predicting the GTEPs based on that graph and configuration pair. So the configurations are listed here as well, where for data placement, it could either be on device host, some thread block size value, and as previously defined, some eagerness value for register allocation. Our machine learning models were trained using cross-validation, and for hyperparameter selection on our MLP, we look into hyperparameters such as batch size, learning rate, and the MLP hidden layer sizes, as well as L2 regularization values. And our decision trees, we trained separate decision trees based on graph type, those graph types being bipartite, unipartite undirected, or unipartite directed. And once we finish training with cross-validation, we take the best hyperparameters and evaluate on a held-out test set of 10% of our total graphs to evaluate the performance of our models. So now moving on to the results of our paper. For our machine learning models, we use two different metrics to evaluate performance, the first being percentage of optimal. And percentage of optimal is defined as the predicted configuration performance from our machine learning model over the optimal configuration performance, meaning that a value of 1 indicates that the optimal configuration was selected, and the closer we are to 1 for our values here, the closer we are to predicting the most optimal configuration on average from our machine learning model. The next metric that we use is speed up over the default baseline. And this is a similar idea, but instead of dividing by the optimal configuration, instead we divide by the default baseline. And the default baseline is also an already well optimized baseline, so it's not like a poor configuration or anything like that. So the larger the value that we get here, obviously the better. And we see that for our MLP, we're able to achieve 96.33% of the optimal on BFS and 99.4% of optimal on SSSP. And I have it highlighted here for BFS in green and blue for SSSP. Top 3 selection means that we basically give the MLP 3 tries to predict the optimal configuration, where we try what the MLP predicts is the most optimal, and then we try the next one after that and the next one after that, and we see what the actual values were and select of those 3 what the actual most optimal was and compare it to the true optimal configuration. While a top 1 selection just means we take whatever the MLP predicted as most optimal and use that as our only selection. And similarly, we see also that the speed up or the default baseline is highest for our MLP, not only for the top 3 selection, but even in the top 1 selection where it only has 1 attempt to get what the most optimal configuration is. So an argument that could be made is, well, what if we just have some optimal configuration for a given graph set? Like look into a bunch of graphs, unique graph data set, and find what the most occurring optimal configuration is and always use that. Well, we looked into that, and basically it still doesn't outperform, even when looking into the test set, our auto-tuner method using the MLP. As we could see here in our model, if we just select the top config for BFS, which would be this most occurring one, where the configuration is the device, the placement is in the host, we have a thread block size of 1024 and an aggressive register allocation, which occurs 36 times in the test set. If we were to just choose this, we'd end up with an 87.51% performance in percentage of optimal, while even top 1 selection for BFS is 94.36%, which is significantly higher. And if we go into the top 3 selection, it's an even greater difference where it's 96.33%. And a similar story for SSSP, where if we were to only select the most frequently optimal configuration, we'd have 93.55% percentage of optimal, while top 1 selection is 97.66% and top 3 selection is 99.4%. So another interesting thing to note regarding the results of our paper is when we trained our decision tree models, we could extract the most important features from the training. And a common feature that was important across all decision trees, meaning the bipartite, directed, and undirected, was graph volume. And for SSSP, because those were the BFS values, many of the same features emerge as critical for making optimization decisions. But in addition, graph diameter also proved consequential. Graphs with longer diameters and consequently longer dependency chains increase the register pressure. This increased pressure is amortized in the case of a full traversal, meaning BFS, but it's significant in the path discovery tasks embedded in SSSP. Therefore, unlike BFS, for many graph instances, a moderate register allocation policy is necessary. And we could see this sort of appear in our chart here with the number of occurrences for a moderate register allocation for SSSP. So in order to provide some more confidence in our MLPs that those predictions are actually sound and that it's not just getting lucky, we do 10 random weight initializations, and keeping the same hyperparameters that were found during cross-validation, we retrain the MLP using those random weight initialization 10 times, and then we basically do a prediction after those 10 trainings and check the variance of the predictions. So ideally, there would be zero variance, meaning that it always generalizes to the same prediction. And even more ideally, it would be, the most optimal prediction all the time. And in our charts here, we see, particularly for SSSP, there is extremely low variance, and even the variance for BFS is pretty minimal. Only some graphs end up having a significant variance. So in conclusion and some final remarks, in this paper we identified input-sensitive performance inefficiencies for collaborative graph algorithms in unified memory systems. We evaluated machine learning approaches for modeling the relationship between some input graph properties and the performance. We demonstrated that the selected graph attributes and performance criteria are suitable for developing effective machine learning models. And some future work would be to, instead of creating models for SSSP, BFS, and other graph algorithms, we could instead generalize the approach to a larger subset of important graph algorithms. And an acknowledgement, this work was supported by the National Science Foundation through the following awards and equipment grants by IBM and NVIDIA. Thank you.